Okay, the record is on. So now we are back to the part where we already got the displacement. We need to assign them back. And for fearing that you may forget, let me write the code down with the thick letter. This is your Q1, Q2, Q3, and then Q4. We can continue on with the only formula that we have, that is F equal KD, you know. So F equals KD, sorry. This time, if we look at this formula from the member point of view, now you know the D, you know the K of each member, of course, therefore you can get the force. Okay, so let's say for member one, use the thick one. For member one, okay, now the force matrix of member number one, that's one. Okay, it's going to be equal to KD. And K this time is going to be the stiffness matrix of the member itself, like I already mentioned a few minutes earlier. So it is going to be 34 multiplied by 10 to the power 4 over 25. And the matrix of the member number one itself, that's 9, 12, 12, 16. You should notice how I write the matrix, you know, just create a good habit so that you won't make a silly mistake. Okay, break this into 4 sub matrices, and then I got 9, 12, 12, 16. And then the rest should be the opposite. That is minus 9, minus 12, minus 12, minus 16, minus 9, minus 12, minus 12, minus 16. And remember the code for member number one, it is 3012, right? No, there's no need to do that. Let's say I'm going to go ahead and write it. But if it's 3, so that's your displacement number 3 right here. Okay. Okay. So 3 is, don't forget that we need 10 to the power of minus 4 up front. I forgot that. So it's 1.235. The next is 0. So it's 0. And then 1, which is 3.068. And then 2.265. You multiply this. Can you guess what you should have? This is the answer. The first one, can you recall that your member number one is like this? So D1 will be your force at node 1 in x direction, right? Which is minus 26. That's my 2. Okay, excuse me. Let's make it more look more like a 2. 26. Not better, but okay, we will leave 0.26. So minus means that it is going into the minus x direction, right? So here it is. Minus x, 26.76. The second one, we get minus 35.68, minus 35.68. Again, that's minus, so it goes into the minus y direction, like that, 35.68. Can you guys notice one thing? If we are going to find the resulting force from D1 and D2, you should notice that the resulting force will be in this direction, right? So that means these two force components better, have the good relationship amongst each other. Let's say if you have a negative x, which means the force is pointing to the left, you cannot have the positive y. Because let's say if you calculate and then you get this term positive, it would have meant that your force is pointing upward. And when you try to find the resultant, what kind of force you're going to have? Your resultant force will go in this direction. It's not possible, right? And so when you have minus x here, in this case, you should have minus y. So when you sum up the force by using the vector, it will go nicely in the same direction. So this can't happen. Okay, and when you sum the force like this, you should realize that, okay, it is pointing out of the member, so it looks like a tension. Okay, so you bet that now, even without any calculation, you should perhaps realize or expect your force in this x to go to the right, and then y to go up, so that your sigma fx and sigma fy for your member are satisfied. And when you have the case like this, again, when you sum up the force, it is going into this direction. So this just goes to show that your member number one is definitely under tension. Okay, so yeah, as you expect, this is 26.76 positive and 35.68, which positive, so it goes up, confirms our idea. Go to the right, this one, right? 26.76, and the last one, 35.68, it's positive, so it goes up. So that's your member number one. We can do the same for member number two, okay? Member two. Member number two is, let me try to be consistent. Okay, so I'm just going to write the force first. Okay. The force for member number two, okay? Again, we write down the stiffness matrix for member number two, which is 34 multiplied by 10 to the power 4, divide by 25, and it is 9 minus 12 minus 12, 16. Again, I always write like this. So this is 9 minus 12 minus 12, 16. So the rest should be the opposite. So it becomes minus 9, minus 16, 12, and 12, minus 9, minus 16, 12, and 12. The code for member number two is 0012. Okay, so we can come back here. 0012. We need to pick 00 and then 1 and then 2. Okay, this is 1, this is 2. So this time I won't forget, we have 10 to the power minus 4 up front. 0, 0, 1 is 3.068. 2 is 0.0265. You multiply this out and you're gonna get, the first one is minus 33.23. Okay. And let's say our member number 2 is like this. And the code is, this is your local node 1 and this is your local node 2. So the first term minus, so it goes into the minus x direction, right? 33.23. So what do you expect? It goes like this. So you should expect your y to go up to form compression, right? And rightly, okay? The answer for this is 44.3. It's positive. So it is going up. 44.3, and therefore goes to show you that let's use the red one, feels like compression. You guys get compression for this, okay? And that means if we come back and try to expect what you should have at your node 2, it should give you compression and then perfect equilibrium. So it should be like this, right? Okay, and it is indeed like that. So for D3, that's 33.23 and minus 44.3, which confirm what we should have here. Okay, positive x, it's 33.23 and negative y. So it's coming down 44.3 and gives you the resultant of a compression. So that's your member 2. Okay. And I think you get the picture now. So I can just go ahead and give you the result for member 3. Member 3, because it is a vertical member. So what do you expect? The force for member 3, you can only have the second and the fourth component, right? If you have the component in the first and the third one, woohoo, you're wrong. So better be 0. This is minus 8.61, 0 and 8.61. So what is this? The orientation of member number 3 is 1 and 2, okay? So if 1 comes down, 2 goes up. So that means this member is under tension, right? And then we can go on to member number 4, which is the horizontal member. So what do you expect? F4 should have only the first and the third component, correct? 26.74, 0, minus 26.74 and 0. And let's look at the orientation. I think we have the common orientation 1, 2 like this. Maybe I should write 861 here. It is 1, 2. This is positive, so 26.74. This is negative. 26.74. So this is a compression member. Okay, and you know, if you can see the picture of the truss, you should now, you know, expect what you're gonna have for member number 5. You know, because we only have the one horizontal reaction, right? So you better expect that member number 4 and member number 5 have the same kind of force. and you bet they should all come out to be the same. But I have the problem of you know, round off, so I got 26.78, which should be okay, you know, negligible. 0, 26.78, and then 0. So member number 5 also looks like this, with let's say 26.7. Okay, so now we can assemble everything and you're gonna see the whole picture. Okay, now when I write member number 1, I have 26.76 here, and then I have 35.68, right? And I'm trying to figure out how I should write so that it doesn't bother anything. Okay, doesn't matter. 26.76, and this goes up. And then member number 2, $23.23, and this is 44.3. Okay, and right here 33.23, I keep saying 23, goes up 44.3. Now when you begin to assemble, you should see that everything must be under equilibrium. So you got that 8.61 here, and that it is 8.61. So you see your equilibrium of the joint in y direction, this should be 0. And then this is what? Is equal to 60, right? That's your external applied force. Okay. And let's move on to member number 4. Oops, sorry. Member number 4, you have this 26.74. You know, it's just when you sum it up, you should consider that to be 0. Okay, round off problem. And then here it's another 26.78. You know, that is 26.78. So you should see that again, this is close enough to 0 because you have a roller, and then this becomes your reaction. Okay, this is close enough to 0 as a roller, and therefore this is your reaction. Okay, and then you see this is also your reaction, and this sums up equal to 60 because your reaction here needs to be equal to 60, right? So once you figure out all the forces acting on your members, you can proceed to obtain the reactions by considering the structure that you have as well, you know. And I can tell you now that there is more than one way that you can handle this. Some have the way to write their matrices to include the reactions and everything in the system, like entirely. That is okay, because I think most of you who are in the classroom tend to do what I do, because I think this is very convenient enough. I try to use the most convenient one. But there'll be some students who do not show up here, they rather go through their own pain and self-study, and they may pick up some textbooks with different approaches. That is also okay. You know, all right, so that's it. I think we have plenty of time, so let me try to show you another example to demonstrate the fact that the size of the matrix of the structure or the entire system should have the relationship with the degree of freedom of the structure. Okay, so let's go. I have another example. One moment. Okay, looks crazy enough. You guys, no need to get serious about this, okay? So I may not give you every information. Oh, here we go. Okay, we're back in business. So this structure, we have something like this. Okay, 1 trust member, 2 trust member, 3 trust member, 4 trust member, 5 trust member. That doesn't look very solid. Ooh, okay, try again. 5 trust member, 6 trust member, 7 trust member. Okay, and we have the support, a hinge here, a hinge there, and then a roller here. So the key is to identify the degree of freedom of the structure. Okay, how many do we have here? So let's say we are going to have Q1 here, and then Q2 here, so that's 2. Then this is this one is not a joint, okay? This is just 2 members crossing each other, so this is not a joint. Then we have Q3. Then we have Q4, and then this is a roller, so which means you are free to move in the horizontal direction. So we have 5. But in this, we have 5 degrees of freedom, okay? So in the end, that means you need to have a 5 by 5 stiffness matrix of the structure. If you fail to identify this, you're in the fatal situation. Okay, so I'm not gonna go through and finish everything with this problem, but what I can do is that I can try to give you the local node for each member and see, we can work our way to see if you can construct your code matrix, okay? Stuff like that. So let's say this is my member number 1. Okay, and I'm gonna give it local node 1, 2. So, you know, if you do this, because you should generally give the numbering to every member before you start doing the code, but I'm afraid that it may get a little bit messy. So I'm just gonna go ahead and do it while we are giving the label and the numbers to the member. So if this is the local node for your member number 1, what is going to be the code matrix? Okay, so the code, we can do it right away. Node 1, you can see it's a hinge, so it's 0, 0, right? And then node 2 involves with the 2 degree of freedom, so it's 1, 2. You see, not that difficult. So we can move on to member number 2. Let's call this member number 2. And let's say local node 1, 2 is like this one. So again, when you look at member number 2, local node 1 is the hinge. So your code should be 0, 0. And then your local node 2 is right where you have degree of freedom Q3 and Q4. So it becomes 3 and 4. Right? And let's move on and locate member number 3. So let's call this one member number 3. And I'm going to use the same local destination for member number 3 so that we have a easier option when we are writing the stiffness metrics. So let's use this 1, 2 as well. So for your member number 3, when you consider the code, your local node 1 of your member number 3 is right where you have degree of freedom Q3 and then Q4, right? And local node 2 will have Q5 and then nothing. So it's 5, 0. Okay. Now let's move on to member number 4. I'm calling this one member number 4. Okay. And my local node shall be, this is 1 and then that is 2. So the code for member number 4, local node 1 is here. That means we have Q3 and then Q4. Move on to local node 2. We don't have any movement because it's a hinge. So it's 0 and 0. And now let's move on to member number 5. Let's, 5. I use this one because it's similar to 4 and the same local node, 1 and 2. So for 5, is it confusing? Local node 1 is where the roller is. And in X direction is Q5, right? In Y is nothing. And at local node 2, again, in X is Q1, in Y is Q2. So that's for your member number 5. Number 6, let's call this one number 6. With the local node 1 and 2, okay? So for member number 6, local node 1 is right there where the hinge is. So it is 0, 0. And local node 2 is where you have Q1 and Q2. So it becomes 0, 0, 1, and 2. And the last one, member 7. Right here is, let's use the typical local node. So let's call this 1 and that 2. So 1 is down there, 2 is up there. 1 is where Q3 and Q4 is. So it becomes 3 and 4. We move on to local node 2 so that you have 1 and 2. So it's a little bit tricky when you look at the member number 7. We could have a 1, 2, 3, 4 as our code, right? But if you choose to use 1, 2, 3, 4, the vector for your member number 7 will become, let's say alternatively, if your member number 7, you use this kind of local node 1, 2, your orientation is going to be, this is 1, this is 2, so it's down here. So you're going to have the negative sign instead, right, of this. So you can do that as well. And this, if you use this, it's going to affect your code. It's going to become 1, 2, 3, 4 instead of 3, 4, 1, 2. So once you have the code, it just, wow, I don't have that with me. But anyway, let's because we have some time to play. So let's move to member number 1. I'm not gonna go through every calculation, okay? Just focus on how we can use the code to assign your components from the member stiffness metrics to the structure stiffness metrics and so on. So let's say member 1. Use back. Member 1 is Actually, it's the same for member 1, 2, and 3, right? Yeah. So we have the orientation like this. That is 1 and that is 2. Again, if you are consistent enough, this is your local node 1 points towards 2. So that's basically your x-axis, and your cosine is therefore equal to 1. And then your sine is 0, right? So you're going to have something to multiply up front, but I didn't want to go through that. So it becomes 1, 0, 0, 0 for your submatrix number 1. And then the last one, it's also 1, 0, 0, 0. And you know, the rest should be opposite, so it's minus 1, 0, 0, 0, minus 1, 0, 0, 0. So for the first one, okay, use our code. It's going to be 0, 0, 1, and 2, 0, 0, 1, and 2. So this one, for member number 1, it will turn into 1, 0, 0, 0. Okay, this is from the member. But remember, this time we have 5 degrees of freedom. So you better have a 5 by 5 matrix. And this comes directly from that. Okay, the rest should be 0. So that's going to be for member number 1. Okay, for member number 2, the code is now 0, 0, 3, 4. 0, 0, 3, 4. So again, actually, it's the same submatrix that will come, but it will go into a different region. Okay, so I'm trying to be immaculate. Okay, 1, 2. You don't have anything in row 1 and in row 2. In row 3, we're not going to have anything until this, right? This is the 3rd row and the 4th row in the 3rd and the 4th column. So in fact, this 1, 0, 0, 0 come from that. The rest is 0. It's like playing games, you know, sort it out, run something like that. And then for member number 3, again, let's come back here and erase the code. And now we are going to impose this one, which is 3, 4, 5, 0, 3, 4, 5, 0. Okay, so this one is going to be this one, right? So again, the first row and second row, nothing. And then the first and second column, nothing. And then you shall have this coming from that. Oh, you know, one moment. This is in the wrong direction. Okay, and then that. So yeah, it's 1, 0, minus 1, 0, 0, 0, and then minus 1, 0, and 1, and so on and so forth. Okay. I think we still have time, but you know, I think you got the idea. So would you like me to carry on?
Carry on ค่ะ
Thank you for your response. Okay, so okay, let's try member number 4 and 5. Okay, member 4 and 5. 4 is like this, and oh, okay, not a good job. 4 is like this, and to give some number so that you can see better, let me come back here and give some dimension. Okay, this is 6 meters long. That is also 6 meters long. The height is 4.5. Okay, so for member number 4, 4.5 and 6. So basically, again, that's a 3, 4, 5 triangle, my favorite one. Okay, sorry. Right. That's 3, that's 4. So that's 5. But the orientation of this is 1, 2 like that. So you be mindful, okay? 1, start from 1, points towards 2. So you're in quadrant number 2, okay? Quadrant number 2 means that your cosine is negative and your sine is positive. Okay, so cosine is minus 4/5 and sine is 3/5. Okay, you should know that some little trigonometry rule, right? This is the same angle, but for the triangle on the left, this cosine theta is equal to minus cosine. I don't know how. Can you recall your trigonometry? This is to write it more perfectly. This is pi over 2 plus theta, right? If this is your theta, this becomes your pi over 2 plus theta, right? This is equal to minus cosine theta, something like that. Okay, if you are pretty good at that, it's no problem. Or you can just, I remember that my very beloved math teacher teaches me this. You just remember this. This is your quadrant, right? In quadrant number 1, everything is positive. In quadrant number 2, everything is negative. 3, everything is negative. So in quadrant number 2, your cosine is x, your sine is y. So in quadrant number 2, your cosine is always negative, your sine is positive. But in quadrant 4, your cosine is positive because it's x, and your sine becomes negative because it's y. You can always use that as well. You know, I used this since I was like 14 years old, maybe 15. No problem in my life about trigonometry. Okay, right. So we can come back here and use this. So for number 4, your cosine is this. So it is, I'm gonna take the 1 over 25 out, okay? And then cosine, that's 16. Sine cosine becomes minus 12, and then 9, okay? And a good habit, I'll do this. 16 minus 12, 9. And okay, the rest shall be opposite. So if this is 16, it's minus 16, minus 9, 12, and 12. Minus 16, 12, 12, and minus 9. If it is member number 4, member number 4 has a code here, 3400, okay? So you just impose 3400 there, 3400. So what you have for member 4? You have just the first quadrant, first submatrix, whatever that is called. 16 minus 12, minus 12, and then 9. The rest is 0. Okay, so 0, 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0. Okay, and then we shall do member number 5. Okay, member number 5, let me go back and use this. Code for 5 is 5, 0, 1, and 2. So it's a bit tricky. Okay, but if you are mindful, if you can concentrate, let's take care of the 1, 2 first, okay? This submatrix right here. So it's 16 minus 12, minus 12, and then 9. So you take care of the first area, and then you realize that there's nothing until the 5th. So it goes 0, 0, 0, 0, and then the 5th. First row, 5th column, minus 16. Second row, 5th column, 12. See? And nothing in 3 and 4. So it's 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And then the 5th row, it's right here, begin with number 1, that's minus 16. Column number 2, it's 12. And then nothing, nothing. And then column number 5 is 16. You see, still symmetric. All right.
Teacher,
Yes.
the member 4, the 16 should be 3, 3. I mean, the location of the 6.
The code for member number 4 is 3400, right?
Yes.
So, oh yeah, you're right. Yeah, you're right. It should be here, right? It should be here. Sorry. And that one should be 0. You're right. I'm just too casual. So yeah, 3400, right. This is minus 16, 12, 12, and then 9, right? That should be 0. Thanks a lot. Okay, right? And we can move on to member number.
It should be 16 minus 12.
Oh yeah, it's yeah, I think that's a mistake. Yeah, it should be plus 16. Right. Wow, it's just a little bit confusing. 16 minus 12, and then 9. Okay. Now you can cursor. And 16 is a little bit dirty. Let's rewrite again. 16. Okay. And you know, now I think you get a grip with it now. And for member number 6, now member number 6 is you know, a typical of member 4 and 5, because if you look at member number 6, oops. If you look at member number 6, it's typical 1, 2. So sine and cosine should be positive for member number 6. Okay, so that means if I can use this and try to be a smart engineer, you know, erase this. Now keeping in mind how the sign is going to change with the 6 The code for 6 is 0012. So for member 6, we are going to have, now it should be all positive, right? Because sine, cosine are positive. So the submetrics in this quadrant and this should be positive. So using 0012, I can now have 16, 12, 12, and then 9. The rest is 0. You know, it's like playing games, really. You should have fun doing this. Right? And then member 7, it's oops, this one with the orientation 1 and 2, but I remember that this is tricky code, so it's 3, 4, 1, 2, right? So let's write the code for this. This is 1 and 2, so it goes up like this. So this means cosine is 0, sine is 1. And the stiffness matrix for the member itself is 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. And the code is now 3, 4, 1, 2. 3, 4, 1, 2. So for member 7, let's do 1, 2 first, okay? Right here. So it's 0, 0, 0, 1. Finish that. We all have business with 1, 2, 3, 4. So this is the first row, and then 3 and 4. 0, 0. Second row, 3 and 4. 0, minus 1. Okay, and then it's up to you what you want to do. You can do row 3, 1, 2, 3, 4. It's all 0. And then row 4, 1, 2, 3, 4. 0, minus 1, 0, 1. So it's probably, you know, let's finish this first, you know, just fill in the zeros. So it's probably going to give you the same if we swap the local node to 1 and 2 like this. And then your sine will become minus 1 instead. You're going to end up with the same, maybe. Okay, so I think that's that. So you can sum them up, and therefore you can get your stiffness matrix for the structure. Okay, so this I hope that this example serves as well to show us that the stiffness matrix for the structure doesn't have to be 4 by 4. The size of the stiffness matrix should always, you know, reflect the degree of freedom that you have. So in this case, because we have 5 degrees of freedom, we shall have a 5 by 5 stiffness matrix. Okay. So is there any question? The rest is just the same. Is there any question, folks? If you don't, believe it or not, that's the end of the matrix. That means we can have our tutorial with the matrix tomorrow, I think I'm gonna make an announcement on Facebook again. But before we talk about that, let's stop the session. Let's stop the video if you don't have any question. Okay. I suppose not. It's straightforward enough.